Hi, this is a video for Chapter 11 homework. Chapter 11 is talking about the fluids. Before we look at the homework problems, I'd like to give you a quick summary about the important things of this chapter. So here I list the several equations, and let me just go through each one of them. The first thing we look at is that we talk about the density. So the equation to find out the density, which is a rho, that is equal to the m over v, where the m is the mass, v is the volume. Sometimes we will use weight density. If we use weight density, then you can replace the m by the weight. Notice that unit, that if you use SI unit, it's going to be kg meter cube. If you use a different unit, such as using the CGS, that will be gram per centimeter cube. So this is the unit for the MKS. This will be the unit for the CGS. The second thing we look at is the pressure. Now the pressure can be computed by two different ways. The first way that we decided what the pressure is that we look at the force that is perpendicular to the surface and divide by the area. So force perpendicular to the surface divided by the area is our pressure. Now the unit for the pressure is going to be Pascal, which is simply equal to Newton divided by meter squared. Or if you use US unit system, that will be PSI, where the PSI represents a pound per inch squared. Now we have several different unit systems we can use for pressure. We can use ATM, which represents atmospheric pressure. Or you can use millimeter of mercury. There is a conversion factor how you can convert all these things. So you can look at book to know all these values. The second definition that we give you for the pressure is that you can make it more general. If you know one point with the pressure P0, then somewhere else, which around this P0 position, you want to find the pressure at that position. Normally this position will be lower than the P0 position. Then the P lower that you try to find is going to be equal to the P0, which is the starting position, plus the rho GH. I want to emphasize this rho here. This rho is the rho of the fluid. It's what is the fluid that you are looking at, the pressure that is coming from. It could be air if you are in the air. If you are underwater, then this P0, this rho will be the water density. If you put things under oil, then this rho will be the oil density. D here represent the depth, which represent how much of the distance that below the P0. So that is the second way that we can find out the pressure. Okay, let's move on to the next one here. So what happens if you have a pressure difference? If you have a pressure difference, then what happens is that you could have a force. This force is due to the pressure difference. So the force is going to be a net force due to two different pressure force. For each one of the pressure, we'll give you a force, and how do we get the pressure force? It's based on the definition that we give you, the P equal to F perpendicular divided by A. So F is simply equal to the pressure times the area. So P2 is larger pressure, P1 is the lower pressure. The pressure difference gives you the force, the direction, is from the high pressure to low pressure. So that is the direction of the force. Okay. Now the force is the Newton, so that's the same as we used before. After that, we talk about the buoyancy. So this is an important topic because we did a lot of example in the class already. I want you to remember the rules. If you have a float object, then the weight is equal to the buoyancy force. So our buoyancy force is F of B right here. If you have something sink down to the bottom, then the buoyancy force will be less than the weight. And if it's down to the bottom and the bottom will give a normal force, then the buoyancy force is equal to the weight minus this n here, where n is the supporting force or the normal force. Now this situation might change if this is not sink down to the bottom. But to fully understand this, that you need to know how to draw a free body diagram, and we did a lot of example in the class already. You should know how to do it. The other important equation related to the buoyancy is the Archimedes principle. So Archimedes principle is very simple. It simply said the buoyancy force is equal to the weight of the displaced fluid. And what is the weight of displaced fluid? It depends on the volume being displaced. Well, the volume itself is not the weight. How do you get the weight? It will need to multiply with the G, so that G multiplied with the mass is going to be the weight. And this part, the density multiplied with the volume, is our mass. So the mass times G is the weight, which is the buoyancy force. This works for fully submerged or partially submerged. Any of the object is even it's sink down to the bottom, you also use the same way to calculate the buoyancy force. It only matters about the volume displaced and also the density of the fluid. So this is what we call the Archimedes principle. Alright, after this, then we start to look at what happens if the fluid will be in motion. If fluid is in motion, then we looking at the flow rate. We define the flow rate. Remember, the Q here represents the flow rate. And the flow rate is simply equal to the change of the volume over change of the time. It's in certain period of time, how much volume of the liquid will flow through. That is our flow rate. Starting from the flow rate, then we define an equation based on the conservation of the matters. So that means how many of the fluid goes in will be equal to how many of the fluid goes out. We get this equation based on the flow rate definition. And the way that we define this is that you can make this one change to be the area times the distance. So that will be the area times the distance over the time, where the distance over the time is our velocity. So that's why we have the AV. So your flowing material, the flowing rate should be equal to the flowing out rate. The things goes in should be equal to things goes out. And that is the continuity equation. The second important equation is called the Bernoulli equation. We explain this phenomena in several different ways. We talk about the blood vessel, we talk about the house roof blow out from the high wind. This also explains why the airplane can fly with a lift. This is all coming from this Bernoulli equation. Now, a very simple way to remember that is the Bernoulli equation has three things combined together is a constant. And the three thing is the fluid pressure. The second thing is due to the kinetic energy. And this kinetic energy, by replacing the mass by a rho, we can write this equation to be like an equivalent pressure due to the kinetic energy. So that's 1/2 rho v squared. And the third term is about the potential energy in terms of the pressure. And that is we replace the m by rho, and that will be rho gy. So these three things add together will be a constant. So that is what we call the Bernoulli equation. When you do this kind of problem, whenever you have this conservation things, then you look at the two different points and you get information for each one of the point. Use something together and make them equal, then you can solve for a number. The last thing about this chapter we didn't spend a lot of time talk about is the viscous flow. I just need you to know how they are related. So if you look at the equation, you know what exactly they represent, how will the things affect the other property. You look at the Q here, which is what we defined before, is the flow rate, is the volume flow rate, is how much of the fluid in volume flow through in certain period of time. That is equal to the pi r to the fourth. Okay, this is to the fourth. This is not to the square. We use square a lot, but this one is to the fourth. And divide by 8 eta L. So the L is the length of the pipe, but the eta here is the viscosity. Okay, the viscosity. We didn't talk about viscosity a lot, but if you have water as opposed to you have a grease, then you know the grease is more viscous than the water, so the viscosity will change how the fluid is flow. The blood is more viscous than water, so it will flow slower, the flow rate will be smoother. So how are they related is based on this equation. Higher of the viscosity, then this number will be smaller, that means the flow rate will be smoother. The larger of the radius make the pipe to be a larger radius, then you will allow the fluid flow more easily, then you're going to have more flow rate. And also, how would the fluid flow? The fluid flow was because of the pressure difference. Because there is a difference of the pressure, then it will drive the fluid to flow. So it will flow from high to low, and this is your driving force to make the fluid to flow. Okay, so this is something that I want you to know for this chapter. And let's look at some of the example by looking at these things follow. Now the first homework problem that I wanted to show you is about the density. So over here the problem says what is the average density of a cylinder that is 30.0 centimeter long and 1 centimeter of the radius. So what that means is that you have a cylinder like this, just like the cylinder that you did the lab, that you have several cylinders with a different metal, right? So this is a cylinder, and they give you the radius of the cylinder. So this is the radius of the cylinder, and the radius is equal to 1 centimeter. The length of the cylinder is 35 centimeters. Okay, and we want to find the density. Now the density that we know is equal to the mass divided by the volume. Well, the mass is given, all you need to do is to find out the volume of the cylinder. Now remember, the volume of the cylinder is equal to the area multiplied with the length. So what is the area? Area is pi r squared, and you multiply with the length, and that is the volume of the cylinder. And you use this volume of the cylinder in this equation, and you can find out the density. And be careful about the unit. If you ask for the unit of the CGS, it will be gram per second cube. Okay, the second homework problem I wanted to talk about is about the pressure. So it tells you that you have a nail. This is a nail, and there's a nail head of the nail, and this is the body of the nail, and at very end of the nail, it has a point position here. Now, and they tell you, well, this head of the nail has 0.35 centimeter diameter. Okay, this is the diameter, this is not the radius. And you use a hammer to give a force, so the force that you give is 40 Newton. And we want to find out, well, what is the pressure that you apply to this nail head? Okay, so if you look at the nail head, you need to find out the area of the nail head. So the pressure at the head is equal to the force divided by the area of the head. And they also ask you, well, what about the pressure at the bottom near the tip, the pointed tip here? Well, and then if you apply the same amount of force, then this pointed place will have the pressure with the same way, but you are going to use the same force. However, you're going to do a different area, so this will be the pointed place. Okay, and that has a diameter which is 0.032, which is much smaller than this. Then you can find out the pressure at that point. Now be careful, you might need to do a unit conversion because this is centimeter, so you have to convert the centimeter into meter, so then your pressure will be in Pascal because it's a Newton divided by the meter square. This will be also Pascal as well. Alright, the next problem is a diver that below the surface of the ocean. We mentioned this in the class. So what happened is this is like a sea level, and this is the ocean, and a diver is below the sea level, and the distance of the diver below the sea level they give you is 20 meters. So that's 20 meters here. Now there's a pressure in the air. This pressure in the air is 1 atm. And they also tell you, well, the density of the seawater, that is equal to 1.02 times 10 to the 3, and this unit is the kg of a meter cube. So you want to find the pressure below certain point, and we tell you if you want to find the pressure and that is a different position at a lower position, it's going to be the pressure at a higher position plus the rho of the fluid times G times H, where H is the depth. So what is the lower one? The lower one is this one here, is the diver's pressure it will experience. Where the high is going to be the pressure at the sea level, which is 1 atmosphere. And your depth is going to be 20 meters, and your rho is going to be the sea density. G is 9.81, then you can find the solution. Now they ask you two things. They wanted to know the absolute and the gauge pressure, and what is the difference of these two? Well, if you're looking at the gauge pressure, that is equal to the absolute pressure plus minus the atmosphere pressure, minus the atmosphere pressure. So the absolute pressure is the true pressure that include the atmosphere pressure. If you do the gauge pressure, you are going to subtract the air pressure. You only look at the pressure due to the sea water. So that's how you find the difference of these two. Okay, the next problem that we are looking at is the problem talking about the Pascal law. The Pascal law tell us the pressure change in one side is going to be equal to the pressure change at the other side. So the change of the pressure at 1 is going to be equal to the change of the pressure at 2. And how do we find the pressure? The pressure is the force divided by the area. And so you can replace the force divided by the area on the other side, then you got this equation. Once you get this equation, then you can find out, well, if you have the F1 in here, you know A1 and A2, what is the F2 that will be generated? So that's very simple and straightforward. Okay, the number 5 problem is talking about a chrome. So let's look at the problem itself first. So it tells me this chrome is made of gold. Okay, and when the chrome is weighted in the air, that simply tells you this is the what we call the dry weight. So the dry weight is 5.85. So the dry weight is 5.85 Newton. And if you suspend it from a digital balance and lower into the water, the apparent weight is measured to be this one here. So this apparent weight is actually our wet weight. That is 5.33. And we told you in the lab, if you put object inside of a fluid, then the weight of that one will be smaller. And the reason for that is because you have a buoyancy force. So this is 5.33. So the difference is our buoyancy. Okay. So what that means is that if this one is larger, so the dry weight is equal to your wet weight plus the buoyancy force. But what is the buoyancy force? Well, based on the Archimedes principle, the buoyancy force is equal to the density of the fluid times the volume of the object and multiply with the G, where G is 9.81. So what is the object? This is the chrome volume. It's the total volume of the chrome. So we can rewrite this equation by using these buoyancy force and to replace this. So this will be equal to the wet weight plus the rho, V, and G. Alright, so now we are going to use the mass to represent these things um, instead of just use the weight. So if I wanted to represent the dry weight, the dry weight is going to be equal to the mass times the g, right? We said the mass never change. Your weight might change, right? The weight might change because your g might be different, especially if you put in the water. Now you cannot simply use the mass times g is to represent the wet weight. It's different. What about the volume of the crown? Well, the crown has a density, so this density is the density of the gold. And the density of the gold is equal to the mass of the gold divided by the V of the crown. So this is the crown, this is the mass of the crown. Let's make this one to be the crown mass here. So this is a crown mass, this is a crown volume. And when you divide these two, you got the rho of the gold, which is this, which we can represent this one in terms of V sub crown is equal to the mass of C divided by rho of the gold. Okay, so now I'm going to rewrite this. This will be the wet plus my rho of the fluid and times the mass of the crown, rho of the gold, and times G. Okay, so so now I got the I am going to move these things over to the left so I can combine these two together because they have some common terms. They have the NC times G. Here I have NC times G. Then I can represent the wet of this one. That is equal to MC times G, and it will be 1 minus the rho of fluid divided by rho of the gold. Well, what is this one? We didn't talk about this, but let me just explain. What does the specific gravity means? This specific gravity of the number simply represent if you use the density of one object with respect to the density of the water, then the density ratio is the specific gravity. So the rho's of G divided by rho's of water, that is what we call the specific gravity, and which is equal to 19.3. Now if you look at here, this is a reciprocal to that. So when you put this one over here, then it just simply says, well, the rho's of F divided by rho's of gold is equal to 1 over 19.3. Now with that information, you will be able to solve this problem. Okay, so all you need to understand in this problem is that you need to know how do we find out the buoyancy force. And be careful, there's several different density here, like 2 different density. You need to know which density is the correct density. And with this equation, we can either find out the density of the gold if we know this one here, we know the wet weight, which is 5.33. We know the dry weight, which is this one here, and we know the we know the specific gravity. So if you have these two information, you find out the uh, specific gravity. See if that specific gravity is equal to 19.3. If it's not, that means this chrome is not made of the gold. It's made of other material. That's how we determine whether this gold is true or not. Okay, let's look at the next problem. The next problem is about the fluid in motion. Now this is very simple. It just make a graph, and like the one I did in the class, this is a blood vessel that is partially blocked by a plaque. So here is the plaque. It will narrow the flow vessel, and the area over here is going to be decreased by 60%, and the decrease of the diameter by 60%. What does that mean? So if this one is the diameter, this is a D, you decrease for a 60%, meaning you only have 40% left. So if you look at the diameter of here, let me make this one to be a capital. So this one should be a larger diameter. And this one is the smaller diameter. This is only 40% of D. Right? Then what you need to do is to use the equation of a continuity, the A1 and V1 equal to A2 and V2. And you try to find out the velocity. So what is A? A is coming from the diameter, which is a pi d squared divided by 4, and then you can find out the result. The next problem is also about the fluid in motion, and this one particular one is about the Bernoulli principle. Okay, you need to use the Bernoulli equation, which is the equation tells you the pressure plus 1/2 a rho v squared plus rho g h is a constant. And when you solve this kind of problem, you need to find 2 points, and you use these 2-point information made them equal, then you can find out the result that you need. So let's pick 2 points. So the one of the point must be the point that you have something go out. So we're going to pick one of the point, which is just right outside of the hull of the tank, and here. And we have another point we have to pick, and the other point that we will pick is that you look at the information. What is the place that you know about the pressure, you know about the fluid velocity, and also the height. And the point I will pick is going to be the point at the top of the tank. So at the top of the tank, I can find out the pressure, I can find out the velocity, I can also find out what is the height at that point. So what is the pressure at the top? Well, at the top, it's open to the atmosphere, so at the top you are going to have the pressure, which is equal to 1 atm. This is atmosphere pressure at the top. And what is the velocity? Well, this fluid at the top, it will flow, but the motion of the flow is going to be very small. We're going to assume this place is further away from the opening on the right hand side at the opening 2. So we can kind of assume this velocity is going to be approximately equal to 0. So the fluid on the top doesn't really flow, and there is going to be equal to 0. Now what about the height? Well, this height of 1 is simply equal to this height here. If you make the bottom of this one to be 0, so this is a 0, then this will be your h1. So we can use h1 and here as our rho GHH, right? All right, so that's the point 1. Now the point 2 is the point just outside of the hole. At the point 2, this place connect to the outside air, so this point 2 is also have the pressure that is 1 atm because it connect to the air, to the open air. Well, the velocity of 2, you can see obviously that is not going to be equal to 0. That's something we try to find out because it's flowing outside. Well, the height of the 2 is going to be different, right? So what is h of 2? Well, h of 2 is the height from here to here. This is your h2. You put all these things into this equation, and what you need to do is that you need to find your v. Okay, use this equation to find out v sub 2. So once you find out v sub 2, the problem is not asking you about the v sub 2. They ask you if this one is flowing out, where will the water land on the ground? What is the x? Then the water will reach to the ground. This problem turns out to be the problem of kinematics. So it is the same problem like you have a ball that go through a projectile motion and goes to horizontally and then on the ground, and I wanted to find out, well, what is the distance from here to here? You given with a velocity v sub 2, and you want to find out what is the x. So it's a projectile motion. Projectile motion, you have x direction, you have a y direction. The x direction is a uniform velocity motion, and y direction you are free fall. Okay, notice the height here is h of 2, which is equal to the h1 minus delta h. Okay, you given with delta h, you given with h1, you can find out what h2 is. And when you have a uniform velocity, what does that tell you? Uniform velocity meaning if you have a distance of x, the velocity, which is the velocity of the v2, is going to be equal to the change of x over change of time. And this x is the x that you try to find out, is this one here. Now you don't know the change of time. How do you know change of time? The time when this time is the time when this one reached to the ground. So you have 3 equations. Which equation should you use? You need to get the equation with the information of time because you need to find the time. You have information about the height. So the height is going to be the y1 and y2. And you don't know the final velocity in the free fall, so you probably don't want to use the equation with the velocity because you don't know the final velocity. You do know the initial velocity at that direction in the y direction. Velocity at the y direction initially is equal to 0 because it only goes horizontally, it doesn't go vertically, so this one initially is equal to 0. But you don't know the Vy of the final. So that is how you're going to solve this problem. The last problem I wanted to take a look is the syringe problem, and let me just draw a picture, and then you think about what you have to do. So you have a syringe. So this is a syringe. Um, and there's an inner diameter. So the inner diameter is this one here. When you use a syringe, they have a number for different kind of size of the syringe. I don't remember exactly what the number represent, but you can look online. You can see when they say like a 25 number 25 needle or number 10 needle, that represent different diameter of the needle. So a nurse uses the syringe to inject a fluid, right? So you inject you give a force. So this force applied to the syringe, you will see a piston inside of the syringe. So when you apply a force to the syringe, you are going to give a pressure. That means you're going to give a pressure. And you are injecting this one to a patient's artery. Now the artery, let's say this is an artery. The artery is going to have a blood that is flowing, and it's going to be against the needle, and how much of the blood pressure is going to be based on these two numbers. So one of them is the 140, which is the blood pump out, right? So you are going to use the 140 to represent the highest the pressure that the needle has to be against in order to inject the fluid inside of the syringe. So you have this pressure here, which is 140 millimeter of the hydrogen of the mercury, and we want to find out what is the minimum amount of force that you need to apply in order to inject this fluid into the blood vessel. So how do we do this one? Well, you simply just need to see if this pressure is higher than this pressure or equal, then it will be able to inject the fluid. So the minimum force is when this pressure that you you do the injection will be equal to 140. So what is the injection pressure? The injection pressure is going to be the force minimum divided by the area. That will be equal to the against the pressure, which is 140 millimeter of mercury. Well, this force here is in Newton. The area is going to be changed to meter square. It's not the same unit as the one that you see, which is a millimeter of the mercury. So you need to do a unit conversion. So the unit conversion for this one is that you're going to use 716 millimeter of the mercury is going to be equal to 1 atm, and this 1 atm is equal to 1.01 times 10 to the fifth Pascal. So what you need is actually this one here and this one here. Then you can convert this one into the Pascal. Then you can find the minimum force they needed to do this injection. Okay, so this is probably the most important part about this homework, and I hope that you be able to solve all these problems. And if you have any other question, please contact me, and then I can walk you through the problem.